Hello and welcome to this presentation related to second moments of area. This is an introductory presentation to the topic. In this presentation we will calculate second moments of area about various axes of our section and also calculate the associated radius of gyration. So useful background knowledge. There is a separate presentation related to the calculation of centroids of area, where we calculate the respective x bar and y bar for a section using first area moments. And the approach used does provide some background knowledge related to this presentation. Some further useful background knowledge relates to integration using standard forms or standard table above. We'll be using standard integration initially within the presentation to derive a few formulae, although it's not extensively used within the presentation. And from our standard integral table, it's only the ax to the n integrand we'll be considering. Here's an overview of the current presentation. We commence with a very brief introduction to second moments of area, conventionally given the symbol capital I. Then we define the radius of gyration. K is equal to the square root of I divided by A. That's the second area moment divided by the area of a cross section. And for reference, we'll compare this to the radius of gyration associated with rotating masses. Next, we define the parallel axis theorem, where we can find the second area moment about a datum axis. Now in the second area moment of the section, its area and its y distance squared. We'll define all these terms within the presentation. Then we have example 1. It's an application of the parallel axis theorem. The section considered here is a semicircle. Then next we have a table of typical standard section properties to show you how engineers calculate second area moments in practice using standard reference sources. Then we define the perpendicular axis theorem, as shown here. And I show an array of unity bracket conversions. Sometimes students find it difficult to convert, say, from millimeters to the 4 to meters to the 4 or centimeters to the 4, etc. And the unity bracket method allows a structured way to undertake your conversions. The remainder of the presentation relates to an array of exercises, the majority of which show fully worked solutions. And here are the approximate start times related to the various sections shown on this slide. Should you directly want to review a specific section, but please note most times are generally rounded to the nearest minute. And here is the approximate start times for exercise 1, exercise 2, should you want to review a specific solution. Here are the approximate start times for exercise 3 and exercise 4. Here are the approximate start times for exercise 5 and exercise 6. Again, all times generally rounded to the nearest minute. For exercise 7, exercise 8. And finally the approximate start time for exercise 9, which is left for you to solve at your own pace. Let's now introduce second moments of area. The second moment of area, usually given the symbol capital I, of a section is a property which measures the efficiency of a beam shape with regards its resistance to bending. Again, there's some useful background knowledge here. In a previous presentation we considered simple bending, showing a beam being bent, for example, into the shape shown on the diagram about what's termed its neutral axis. And within this study we considered simple beam theory, also referred to as engineer's bending theory, and the formula is stated at the top of the slide of m divided by I is equal to sigma divided by y is equal to E divided by R. And the I in this formula, shown here, is the second moment of area about the neutral axis of the beam, having the unit of the meter to the 4, or can be millimeters to the 4, etc., and relates to the bending stiffness of the beam. So the second moment of area is a fundamental property when analysing simple beams in bending. And for reference, when we refer to the neutral axis of a simple beam in bending, we refer to this location here on the beam It's your position within the depth of the beam where there is no strain, no extension or contraction of the beam. So the neutral axis of the section or the centroidal axis of the section relates to the same location when considering simple bending. So if we now consider the second moment of area for the elemental strip shown in figure 1, here's figure 1, here's our elemental strip, area dA, about the base of the rectangle, it is determined by multiplying the strip's area, dA, by the square of its perpendicular distance, y, shown here on our diagram, from its base. And the base of the rectangle is essentially on the OX axis here. So in other words, dA multiplied by y squared is the second moment of area of the elemental strip about the OX axis. To calculate the rectangle's second moment of area about the base, the process of integration is used. It's outlined below. So if we consider the second moment of area for the elemental strip about OX axis, called that as DIOX, that would be the dA, which in this case is the width of the rectangle B multiplied by its thickness dy, BDY, and that's multiplied by y squared. Note within the integration process, the elemental strip of thickness dy is so thin that it can hardly be measured. Just reordering the equation, I've written it as B multiplied by y squared multiplied by dy. Now to calculate the I for the rectangle, we consider the second moment of area for the total section about the OX axis. So now we're calculating not the I of the elemental strip about the OX axis, but we're calculating the second moment of area, IOX, for the rectangle about the OX axis, so the base of the rectangle. Noting that B, the width of the rectangle, is constant throughout the depth of the section, B is taken outside the integral here. So inside the integral we have y squared integrated with respect to y between the limits of 0 and d. The standard integrand of ax to the n format shown in our previous tables. So we have b multiplied by the integral of y squared with respect to y is y cubed divided by 3 between the limits of 0 and d, and inserting the limits we find that the IOX, the second moment area of the rectangle about its base OX, is BD cubed divided by 3. For your reference again, this was the standard integrand we used in the integration process. Just for reference on this slide, I've shown the same calculations on the previous slide for the second moment of area of the rectangle about the base, OX, just using an enlarged view and slightly more detail. So I'll let you review this at your own pace. We'll start off in the same way. The elemental strip dA is B dy, and the second moment of area of the elemental strip shown here is B dy y squared. Next we integrate to find the second area moment of the rectangle about the base, noting B is a constant, which we move to outside the integral, and integrating using the standard form between our limits and imposing the limits. So again, the IOX is BD cubed divided by 3. So just a slightly more detailed solution for your reference. We're now going to consider the second moment of area about the axis labelled as GG of a rectangle. So here's axis GG, and that's essentially the centroidal axis or the neutral axis of a rectangular section in simple bending. So we're calculating the second moment area about the neutral axis. Very similar process as that shown before, except now the axis is shifted to halfway up the section instead of being at the base of the section. So again, I've very briefly outlined the solution for your reference. Just note now that the y distance, of course, is measured from axis GG. So here's the solution. Again, the elemental strip labelled as dA, shown here for this section, is equal to b multiplied by dy. The second area moment of the elemental strip about axis GG, labelled as dig here, is the dA multiplied by y squared. Just rearrange that on the next line, which is dby multiplied by y squared But now to find the second area moment of the entire rectangle about axis GG, for that IG, we need to integrate the dig term between the limits, so this time d upon 2 and negative d upon 2. Referring back to our diagram here, about the GG axis we will have the limit of positive d upon 2 and the limit of negative d upon 2. It's below the GG axis. Again, noting that b is a constant, so it's taken outside the integral. So integrating, we find ig is equal to b multiplied by the bracket of y cubed divided by 3 between the limits of d upon 2 and negative d upon 2. On the next line, we simply insert the upper limit and the lower limit. I'll let you review the solution at your own pace. Just be careful of the directed numbers here. But what we find now is that the second moment of area about the GG axis, the centroidal axis, is BD cubed divided by 12, not BD cubed divided by 3. BD cubed upon 3 is the I about the OX axis for the rectangle, but BD cubed upon 12 is the I about the centroidal or neutral axis of the rectangle. Let's now consider the radius of gyration as associated with the second area moment of a section. The radius of gyration, usually given the symbol lowercase k, is the distance from the neutral axis of the beam section to an imaginary point at which the whole area of the section could be concentrated and still provide the same second moment of area value. Engineers use this k value as it helps simplify their calculations. This property is used primarily in solving column or strut buckling problems and calculated from the formula shown below. So radius of gyration, lowercase k, is equal to the square root of the second moment of area I, can be in meters to the 4 or millimeters to the 4, divided by the cross-section area of the section, A, in meters squared or millimeters squared, etc. There is a previous presentation related to the analysis of struts or compression members where we extensively use the radius of gyration k within the calculations, should you want to see a practical application of its use. And purely for reference here, here's another definition of the radius of gyration, but this time as associated with the moment of inertia of a body. So the radius of gyration, again symbol k, in this context is a measure of the distribution of mass within a body about an axis, and its definition is analogous to the definition of the radius of gyration for the second moments of area. So if all the mass, m, could be concentrated at distance k from the axis of rotation, the correct moment of inertia for the body would be maintained. As I said, this is used primarily in solving problems involving rotating masses. So in this context, the radius of gyration k is calculated from the formula shown below. So k is equal to the square root of I, now that's the moment of inertia in kilogram meter squared, divided by m, which is the mass, and that's in kilograms. And indeed there is a previous presentation related to Newton's second law applied to angular motion where we make extensive use of the radius of gyration in this rotating mass context. Again, that's just for background information. Let's consider the parallel axis theorem. In figure 2, shown here, axis GG, shown here, passes through the centroid of the section, shown here. Axis DD, here, and GG are in the same plane, parallel to each other, and located distance y apart, y shown here. So the parallel axis theorem states that IDD is equal to IGG plus the area A multiplied by y squared. So using the parallel axis theorem, the second moment of area of a rectangle about an axis through the centroid can be found. Indeed, the same process can be applied to any section, but we consider the rectangle on the previous slide. Purely for reference, here's a table of standard section properties that I used when I was in industry many years ago now, and it shows an array of different sections. The first one here is a triangular section, and in the table we have the area given for the section. We have the centroid location. It's actually symbol E suffix X in this particular table. In our previous presentation related to centroids, we use the symbol Y bar to denote the vertical distance to the centroid from the base, and for a triangle the distance EX is the height of the triangle divided by 3. Then notice in the next column we have what's called moments of inertia. In this case it's actually second moments of area. There's often a conflation between these two expressions. Moment of inertia in the past has been used to relate to second moments of area, but we should be definitive in our terminology, because within the same problem, for example a rotating mass on a shaft, we may have both second moment of area and moment of inertia to consider. To analyse the shaft in bending, we may use the second moment of area, but to analyse the rotating flywheel on the shaft, we will use the moment of inertia. So as we mentioned previously, they're different but related properties. So in this case, the second moment of area, notice they've given the second moment of area about the XX axis, that's this centroidal axis. They've stated the second area moment about the IY axis, that's this vertical axis. And they've also now stated the second moment of area about axis AA, this is AA, the top of the triangle, and about axis BB, at the base of the triangle. So for different design considerations, we may need to find the I about these various axes, and this standard reference source shows how engineers would actually calculate these specific values. They wouldn't necessarily work from first principles using integration. Next section here we have the rectangle, and again we're quite familiar with the area being the base times the height, B times D. The EX or the Y location is half the height, so it shows it h upon 2. Just note EX should have been stated as D divided by 2, not H divided by 2, because in the sketch here lowercase d has been used for the height of the rectangle, not H. A slight discrepancy in the original reference source. And then here we have the I about the XX axis shown here. That would be our centroidal axis, which we calculated using integration to be BD cubed upon 12, and that's exactly what they show here. We also calculated the second moment area about the base of the rectangle. They've labelled that as BB here. I about the BB axis is BD cubed divided by 3, which we proved earlier within the presentation. And notice they've also calculated the I about the YY axis, this vertical axis here, which they state is DB cubed divided by 12. And again, we could have shown that formula using integration. So I hope that gives you a little indication of how standard tables are used for plane sections. Just showing you further illustrations in the table. We've got tilted rectangles, got square section, trapezium, diamond shape, hexagon, and our table of standard section properties are continued here. We have an octagon, polygon, a circle, we have a semicircle which we'll be using in a moment. The area is shown as 1.5708 r squared. That's actually pi r squared divided by 2, so they've stated the value to 4 decimal places here. The EX value, or the centroid location from the base, they've stated is 0.424 multiplied by the radius r, and again that's approximation. As with the second moment area about the XX axis here, they've shown it in decimal form, 0.1098 r to the 4, and I about the YY axis here, again shown in decimal format. So those are slightly rounded up values, but reasonable for most general engineering problems. On the following slide we'll now show an application of the parallel axis theorem, and we'll consider the semicircle for illustration purposes. So example 1, given the information, stated below. Got to calculate the second moment of area about the diameter, labelled dd, diameter dd shown here, of the semicircle of radius r, using the parallel axis theorem. And they've actually given us some properties. They're actually from the previous table, but instead of showing the decimal values, I've actually shown the exact values here. So to calculate the area of the section, that would be pi r squared divided by 2 for a semicircle. To calculate the centroid or the y location, they use the notation ex in the table on the previous slide. I'll use convention y here. And instead of the decimal, I'm using the exact value, which is 4r divided by 3 pi. So the y is actually the ex on the previous slide. And the second moment of area for this semicircular section, again, I'm using the exact value here, is actually pi divided by 8 minus 8 divided by 9 pi, multiplied by all to the power of 4. So on the next slide, we'll show how we use the parallel axis theorem to find the second moment area about axis DD at the base of the semicircle, when we can calculate the second moment of area about axis GG, the centroidal axis, and we know the centroid location from the base. Full work solution shown on the following slide. So here's example 1, solution, section property for the semicircle. So from the parallel axis theorem, second moment area IDD, base of the semicircle, is equal to the second moment area about the centroidal axis, labelled GG here, plus the area of the semicircle multiplied by the y dimension squared, y being the centroid location of the semicircle from the base DD. So we're given from the table, area is pi r squared divided by 2, distance y is 4r divided by 3 pi, and the second moment area about GG axis is pi upon 8 minus 8 divided by 9 pi multiplied by r to the power of 4. And again, that's the exact value. In the tables, they gave decimal values that were approximated. This is an extract from the standard reference source showing the semicircle, and you can see areas wrote it in decimal form shown here. Centroid distance from the base is 4r divided by 3 pi. Again, they've written it in decimal form here. Notice they've used e to the x notation. And the second moment of area about the centroidal axis, they've labelled as xx here and stated in decimal format shown here, but the exact value of the second moment of area about the centroidal axis is shown here. The decimal values are obviously slightly easier to use from a practical perspective, but I'm going to use the exact values in the calculation. So now evaluating IDD is equal to the IG added to the cross-sectional area multiplied by y squared. On the next line, I've simply squared the bracket term here, and on the next line I've simplified the values. On the last line, you can see that this term here, negative term, cancels with this term here, to leave us with the second moment of area about the base of the semicircle DD is pi r to the 4 divided by 8. And that can again be written in terms of a decimal format of 0.3927 to 4 decimal places. Note in the actual extract from our section property table that the I about the YY axis is exactly the same as the I about the base of the semicircle. For ease of reference, I've produced this table of section properties of common shapes that we'll be referring to within the following exercises. So I've shown on the left hand side typical section. We start with a square. The area and the centroid location are very easy to find for the square, but I have included on the right hand side here the secondary moment about the XX axis, which is actually our centroidal axis. That's the same as that about the YY axis for a square. So that's b to the 4 divided by 12. I've also included the I about the base of the square, and that's b to the power of 4 divided by 3. On the next line, I've got a rectangle. Again, we can find the area and the centroid location from the base of the rectangle by inspection. But the I about the x-axis, shown here, is bd cubed divided by 12, which we proved in the early part of the presentation. And the I about the y-axis here can be shown to be db cubed divided by 12. And we proved this again in the early part of the presentation, the I about the base is BD cubed upon 3. Further sections considered are the solid circular section, area stated here as pi d squared divided by 4, or of course that could be pi r squared, but d is stated in the figure here. The second moment of area about the x-axis and the y-axis are the same, pi d to the 4 divided by 64. I've also considered the annular section here, the hollow section or pipe section. We have an outside diameter uppercase d and inside diameter lowercase d. So the formula for area is pi outside the bracket uppercase d squared minus lowercase d squared divided by 4, and the second area moment Ix, again the same as the second area moment Iy, and that's equal to pi multiplied by the bracket of the outside diameter to the 4 minus the inside diameter to the 4, all divided by 64. I've also included the semicircular section. We've reviewed this section previously in the presentation. Area stated as pi r squared divided by 2. R is the radius of the semicircle. Notice I have stated here the y bar, the y dimension shown here to the centroidal axis. I've actually stated in two forms. The first one is the exact value of 4r divided by 3 pi, or as stated in the reference source, y is approximately equal to 0.424r. I've also stated the IG, that's the I about the centroidal axis shown here, GG, and the exact value of IG is pi divided by 8 minus 8 divided by 9 pi, and that's all multiplied by r to the power 4, and the approximate value for IG is 0.1098 r to the 4. And I've also stated the second area moment about axis BB, that's the base of the semicircle. The exact value we proved on a previous slide, pi r to the 4 divided by 8, or IB, is approximately equal to 0.3927 r to the 4. Finally included a triangular section, area BD divided by 2, half base times height. Notice that the y dimension shown here is actually the height d divided by 3, it's a third of the height from the base. And I've calculated various second area moments. For I about the lowercase a axis, that's shown here at the top of the triangle, the apex of the triangle, and that's BD cubed divided by 4. We've got the I at the base of the triangle, that's the lowercase b shown here on the axis, the base, and that's BD cubed divided by 12. Then we have the I at the centroidal axis, labelled as GG, and that's BD cubed divided by 36. And finally we have the I about the y-axis, that's shown here, and that's dB cubed divided by 48. So within the following exercises we'll be referring to these various sections to help us solve the respective problems. Let's consider the perpendicular axis theorem. So in figure 4, shown here, axes OX, here, OY, here, and OZ, shown here, are mutually orthogonal to each other. In other words, they're perpendicular to each other. If OX and OY lie in the plane of the area A, then the perpendicular axis theorem states the following. The IOZ is equal to the IOX plus the IOY. So that's the perpendicular axis theorem. Here's a brief illustration of use of the perpendicular axis theorem if we refer back to a previous presentation related to the analysis of simple torsion and our simple torsion formula. Here in illustration A is a solid circular section shaft subject to an applied torque. Within the analysis of such a problem, we often want to calculate the polar second moment of area for, in this case, the solid shaft. In the simple torsion formula, that's actually symbol J. And to calculate the value of J, we need to find the second moment of area about the OZ axis shown here in illustration A. And we can calculate the OZ using the perpendicular axis theorem from the previous slide, because we know that the second moment of area about OZ is equal to the second moment of area about the OX axis shown here, added to the second moment of area about the OY axis shown here. We know from the extract of our section property table below that for a solid section shaft, the IX and the IY are the same. They're both pi d to the 4 divided by 64. So inserting these values into the perpendicular axis theorem, adding the two terms on the right hand side together, we find that the IOZ is pi d to the 4 divided by 32. And that is the value of J we use in the simple torsion formula for a solid circular section shaft. So that's just one illustration of how the perpendicular axis theorem can be used. We'll make use of this theorem in a later exercise. This slide relates to unity brackets. We reviewed this topic in a previous presentation. What I'm showing on this slide are just some of the typical unity brackets we might want to use. So for area, I'm showing a relationship between millimeters and centimeters squared here, between meters and centimeters squared here, etc. On the next line, I'm showing second area moments here between millimeters and centimeters to the power 4, centimeters and millimeters to the power 4, etc., etc. Second area moment conversions continue on the next line, and also conversions for rates of gyration between various units. Because they're linear dimensions, I think these are easier for students to undertake conversions between meters, millimeters, centimeters, etc. Here are some examples of unity bracket conversions for your reference. Here we have a conversion of the second area moment value from centimeters to the 4 to millimeters to the 4. It's labelled as IX here. So the value we're converting is 324 centimeters to the 4. And in this case, a unity bracket that relates centimeters to millimeters is that 1 centimeter is equivalent to 10 millimeters. So that's our unity bracket. Because this unit is raised to the power of 4, then we raise unity bracket to the power of 4. They're also referred to as cancelling unity brackets. So that's why the centimetre is in the denominator of the bracket that's raised to the power of 4. And that cancels with the centimetres 4 here in the numerator. So our final value would be 324 multiplied by 10 to the power of 4. And that gives us a value of 3.24 times 10 to the 6 millimetres to the 4. So in other words, 324 centimetres to the 4 is equivalent to 3.24 times 10 to the 6 millimetres to the 4. That's an illustration of the use of unity brackets. The second conversion below, again for second area moment, but this time converting centimetres to the 4 to metres to the 4. It's the same approach as above, but this time the unity bracket is 100 centimetres is equivalent to 1 metre, and again that's raised to the power of 4. So in this case, 324 centimetres to the 4 is equivalent to 3.24 times 10 to the negative 6 metres to the 4. Again, note the cancelling unity bracket. On the right hand side, we've converted radius of gyration values from centimetres to millimetres. These are slightly easier conversions as they're linear dimensions, but students are sometimes confused as to whether to multiply or divide by a particular value. Again, unity brackets structure the conversion. So here we're converting our radius of gyration, kx, of 5.27 centimetres into millimetres. I'm sure most of you will know that conversion, but the unity brackets structure it for us. In this case, our unity is 1 centimetre is 10 millimetres, so the linear dimension here. So essentially we simply multiply the 5.27 by 10. So the kx is 52.7 millimetres. Again, we have the cancelling unity bracket effect here. I will let you review the final radius of gyration conversion from centimetres to metres. So this is essentially a reference slide related to the type of conversions we'll be using within the calculations later within the presentation. As I said, there's a separate presentation relating to cancelling unity brackets should you want further information. Let's consider exercise 1. We're asked to evaluate the second area moment in centimetres to the 4 and the radius of gyration in centimetres about axes xx, shown here, the centroidal axis, yy, shown here on the right hand side vertical end, and zz, the base, for this rectangle shown in the sketch. Note we also have to state final answers in millimetres to the 4 and millimetres for the second area moment and the radius of gyration respectively, and also in metres to the 4 and metres. And we've got to use appropriate conversions. We'll use unity brackets to undertake these conversions. For your reference, here's exercise 1 and the answers associated with the question. If you're thinking of attempting this question without further assistance, I would encourage you to stop the presentation and do so now, but the full work solutions are shown on the following slides. So exercise 1, commencement of the solution. So we know from the question the width of the rectangle labelled as B here is 12 centimetres, the depth of the rectangle labelled as D is 4 centimetres. If we can calculate the area, A is simply B times D, so the area is 48 centimetres squared. So next we have to calculate the second moments of area in centimetres to the 4. So firstly, to calculate the I about the x-axis, that's actually the centroidal axis, we'll be referring to this formula here, BD cubed divided by 12, so I about the x-axis in this particular diagram. So simply inserting the values for B, D, which is cubed here, we can evaluate IX at 64 centimetres to the 4. I about the y-axis, that's shown here, and that's the base of the triangle. The I about the base of the triangle shown here would be about this location here, would be BD cubed divided by 3. But if we wanted about this location here, then we would interchange the B and the D. So the I would be DB cubed divided by 3. And that's what we're showing here, DB cubed divided by 3. Inserting the values, we find the I about the y-axis is 2,304 centimetres to the 4. The I about the z-axis, shown here on the diagram, would be, as is stated in the table, B d cubed divided by 3. Inserting the values, I about the z-axis is 256 centimetres to the 4. Calculating now the radius of gyration, stating the answers to 4 significant figures here. The radius of gyration, that's the k about the x-axis here, is simply the square root of I about the x-axis divided by the area above, so the square root of 64 divided by 48. So that gives us the k about the x-axis here in centimetres, k about the y, same approach here, it's just going to be I about the y divided by the cross-sectional area, that's 6.928 centimetres, and finally k about the z-axis is I about the z divided by a, 2.309 centimetres. So that's the second area moments and the radius of gyrations calculated in centimetres. Exercise 1, solution continued. This is simply a check of the radius of gyration values, it's purely for reference. We could calculate the kx values, radius of gyration values, by actually inserting the formula for Ix into the equation. It's BD cubed divided by 12, which is divided by the area, which of course is BD, because it's our rectangle here of course. So that simplifies to the square root of d squared divided by 12, and inserting the values. It's approximately 1.155 centimetres, the same as we calculated previously. But within this process we've actually derived a simplified formula for calculating the radius of gyration about the x-axis. It's simply the square root of d squared divided by 12. And we can undertake the same approach for k about the y-axis, k about the z-axis. Develop small formulas that we could use, but of course the answers calculated are the same. That's just for reference anyway. Here's exercise 1, solution continued. Now we're converting the properties from centimetres to millimetres, or centimetres to the 4 to millimetres to the 4. Here's a calculation of the second area moment conversions for Ix. From the 64 centimetres to the 4 into millimetres to the 4. We do the same for Iy and Iz. The radius of gyration calculations are slightly easier. You can probably undertake these conversions without use of unity brackets. I'll let you review the solution at your own pace. And exercise 1, solution continued. Now we're converting our properties from centimetres to metres, or centimetres to the 4 to metres to the 4. Again, I'll let you review the slide at your own pace. Exercise 2, we've got to find the second moment of area, this time in millimetres to the 4, and the radius of gyration, millimetres, about axis PP, shown here, all the rectangles shown. Then we've got to state these answers in metres to the 4 and in metres, using appropriate conversions. We'll be using unity brackets for the conversions. So this will require the use of the parallel axis theorem. We'll need to calculate the second area moment about the GG axis. we'll need to calculate the centroid of the rectangle from datum PP, and then, to say, using the parallaxis theorem, we'll be able to calculate the second area moment about PP. Exercise 2, here's the answer for your reference. If you think you can attempt this question without further assistance, I would encourage you to stop the presentation and do so now, but the full work solution is shown on the following slides. Exercise 2, solution. As always, let's start the solution by extracting the information from the question. The width of the rectangle, uppercase B, is 40 millimeters, shown here. The depth of the rectangle, uppercase D, is 15 millimeters here. And we need to calculate the y dimension, that's a distance from the datum PP to the centroid of the rectangle, through which axis GG passes. So that will be 25 millimeters here, plus half of the depth, 15 millimeters, divided by 2. So that's our dimension y, 32.5 millimeters. Next we calculate the area, A, that will be B multiplied by D, 600 millimeters squared. Now we calculate the second area moment of the rectangle about GG axis. Here's the GG axis passing through the centroid of the rectangle. Referring back to our formula sheet, we need to use this formula, calculating the I about the centroidal axis, shown here. So IG is BD cubed upon 12. Inserting the values, that's 11,250 millimeters to the 4. So that's I about the centroidal axis, GG. Finally, we calculate the second area moment about the PP axis. I put IP here. And the PP axis is the datum axis at the bottom here. So this is using the parallaxis theorem. So IP is equal to IG plus the area multiplied by y squared. Calculated the area and the y above, of course. To insert in the values, I about the PP axis is 645 times 10 to the 3 millimeters to the 4. Exercise 2, solution continued. Next you have to calculate the radius of gyration, K, then you calculate the K about the GG axis and K about the PP axis. So K about the G axis is the square root of the second area moment about the GG axis divided by the cross-sectional area. So that evaluates to 4.33 millimeters, and the same approach for calculating the radius of gyration about the PP axis, shown here. That evaluates to 32.79 millimeters or 32.8 millimeters, just 3 significant figures. We're asked to undertake the conversions, so to calculate the second area moment in meters to the 4, here's our unity bracket we're using. Notice it's raised to the power of 4 here. In this case, IP converts from this in millimeters to the 4 to this in meters to the 4. And we do the same for the radius of gyration, converting from millimeters to meters. I'd encourage you to stop the presentation and just review the unity brackets so you'll clearly understand the conversions. Some students do struggle with these conversions. But that's the solution to exercise 2. Exercise 3, we've got to calculate the second moment of area and radius of gyration for the triangle about both the centroidal axis GG, shown here, and the datum axis QQ, shown here. Exercise 3, here are the answers for your reference. Obviously this time you'll have to refer to our standard table and extract the values associated with the triangle, shown here. I'd encourage you to start the presentation and attempt exercise 3, but the full work solution is shown on the following slide. So exercise 3, commencement of the solution. We're given in the question the section dimensions of B, base of the triangle, D, the height of the triangle. And we can calculate the centroid distance of the triangle. I've referred to this as lowercase d here, but we use y in previous examples. But essentially in this case it's going to be the 60 millimeters shown here, plus a third the depth of the triangle. Again, that goes back from our table. This is a centroid location. It's d upon 3 in this region here. So the value of d is 100 millimeters. We can calculate the section properties of the triangle. We calculate the area of the triangle. That's simply BD divided by 2, so this is the area calculated here in millimeters squared, and to calculate the second area moment Ig about the centroidal axis Gg, from our standard formula that's b d cubed divided by 36, so that property is calculated here. And again, we're using our standard formula to calculate the second area moment about Gg. So to calculate the second moment of area using the parallaxis theorem, I about axis QQ, shown here, is the Ig above added to the area multiplied by what I've labelled as d squared here. So the IQ is shown here. We're also asked to calculate the radius of gyration, k. So here's k calculated for the GG axis, millimeters, and calculated for the Q axis, again in millimeters, both stated to 4 significant figures. Exercise 4, got to calculate the second area moment and the radius of gyration of the circle shown on the right hand side about axis GG, centroidal axis of the circle, and axis YY, the datum axis shown here, 3 centimeters below the base of the circle. Exercise 4 continued, answers for second area moment and radius of gyration shown, and also the section property extract from our previous table for the solid section circle. We can see straight away how we can find the second area moment about the GG axis, actually labelled IX here for the diagrammatic picture shown, but IG about the GG axis in exercise 4, ID to the 4.64. And of course we can calculate the area and the D dimension from G to Y, shown here on our sketch, which will be 3 centimeters plus the Y dimension. I would encourage you to stop the presentation and attempt exercise 4, for the full work solution is shown on the following slide. Exercise 4, here's the full solution. We initially calculate our section dimensions. Here's the value of D calculated. It's basically R plus this dimension here, 3 centimeters. We can calculate the area of the section. We can calculate the Ig value, second area moment about the centroidal axis. This is the centroidal axis GG in this diagram. Then we can calculate the I about the y-axis using the parallaxis theorem, knowing Ig from above, knowing the area from above, and knowing D from above. So Iy is calculated here in centimeters to the 4. And we can calculate the radius of gyration so that you review these at your own pace. And that's the total solution required for exercise 4. Exercise 5, got to determine the second area moment value and the radius of gyration for the semicircle, shown on the right hand side, about axis BB, shown here at the base of the semicircle, and axis XX, its datum axis, shown here, essentially 15 millimeters below the base of the semicircle. Exercise 5 continued. Here are the answers for the second area moments and the radius of gyration. And exercise 5 continued. Here's an extract from our section property table showing the various properties associated with the semicircle. I'd encourage you to stop the presentation and attempt this question, but a full work solution is shown on the following slides. So exercise 5, here's the commencement of the solution. Notice in the question the radius of the semicircle is 0.01 meters, but I'm actually using millimeters here, so that's 10 millimeters. So firstly we calculate the centroid location for the semicircle from the formula here, y is equal to 0.424 r. I'm using the decimal formula from our formula sheet. So that evaluates to 4.24 millimeters. And then to calculate dimension D, which is from the XX axis to the centroid of the semicircle, that will be the 0.015 meters on the diagram, 15 millimeters, added to the Y value. So our D value is 19.24 millimeters. I'll calculate the section properties for the semicircle. The area, pi r squared divided by 2, that evaluates to 157.08 millimeters squared. The I value about the GG axis, that's the centroidal axis, calculated again from the approximate formula for the second area moment. So 0.1098 r to the 4 is a value of 1098 millimeters to the 4. So using the parallaxis theorem to calculate the second area moment about the base, BB, of the semicircle, that's the IG plus the AY squared. So IB is 3,921.9 millimeters to the 4. I've also calculated IB using the exact formula here, a slightly more accurate value, about a 0.12% difference between the values. That's just for reference. Of course, we use the parallaxis theorem here. Exercise 5, solution continued. Now we've got to calculate the second area moment about the XX axis. To do this, we use the parallaxis theorem again. So IX is equal to IG plus the A, but this time multiplied by the D squared, which is 19.24 squared. So here's the value for the IX, second area moment. Then to calculate the radius of gyration about the G, B, and X axes, we simply use the respective second area moment divided by the area. I'll let you review the KB and KX calculations at your own pace. Exercise 6, we've got to calculate the radius of gyration of the propeller shaft, cross section shown, and sketched on the right hand side, and the polar second moment of area. Here's the answers. And exercise 6, here's the section property extract from our table for your reference related to calculating the second moments of area. And of course they'll be the same, IX and IY, and exactly the same formula. So don't forget we're using the perpendicular axis theorem here. So I about the Z will be I about the X plus I about the Y. Full solution shown on the following slides. Exercise 6, commencement of the solution. I'm working in centimeters here. The outside diameter stated as 70 millimeters, that's 7 centimeters. The inside diameter stated as 60 millimeters, so that's 6 centimeters. So we calculate the area using our standard formula here. And I've calculated the second area moment about the x-axis using again the standard formula from the previous table. And as the table stated, the IX and the IY for a circular hollow section are exactly the same, so I'm not really sure why I showed the full calculation here, because we can simply write that the IY is equal to the same as the IX. Exercise 6, solution continued, calculating the radius of gyration about the x-axis. Of course, the radius of gyration about the y-axis would be exactly the same. And finally, the question asks for the polar second moment of area using the perpendicular axis theorem. Not the parallel axis theorem, but the perpendicular axis theorem. And essentially to find IZ, which is the axis protruding directly out of the page here, 90 degrees if you like to the x and y axes, simply add up the IX and the IY values to find the IZ value, the polar second moment of area. Exercise 7, we've got to determine the second area moment and radius of gyration of a rectangular lamina having a length of 40 millimeters and width of 50 millimeters about an axis through one corner perpendicular to the plane of the lamina. Here are the answers for the second area moment and the radius of gyration. If you think you can attempt this question without further assistance, I would encourage you to stop the presentation and do so, but there is a hint stated on the following slide if you're slightly unsure as to what the question involves. Exercise 7 continued. Here's our hint. This shows the lamina and the configuration as defined in the question. Exercise 7 continued. And here's the extract from our section property table for your reference. Obviously it relates to a rectangular section. Now I think you can attempt the question. I would encourage you to start the presentation and do so, but I'll show you the full work solution on the following slides. Exercise 7, commencement of the solution. I'm going to let you review this now at your own pace. We're essentially trying to calculate the polar second moment of area, so we need to calculate the IX, calculated here, and the IY, calculated here. Exercise 7, solution continued. Here's a calculation for the polar second moment of area using the perpendicular axis theorem. So Iz is equal to Ix plus Iy, stated here. I've shown a conversion here using unity bracket from the millimeters value to the centimeters value. That's because the answer was given in centimeters to the 4. And finally we calculate the radius of gyration, k, about the z-axis. So I firstly calculate the area of the rectangle from where I can find the kz value. Calculated here in millimeters and then in centimeters. 2.47 centimeters is the final answer. Here's exercise 8. Got to calculate the second area moment about the xx axis, shown here. For the composite section shown, correct to 3 significant figures. Answer shown here in the bracket. So essentially we'll need to consider this in 3 sections. We have a semicircular section, we have a rectangular section, and a triangular section. So we need to calculate the properties of the various shapes using our standard table, which I'll show you on the following slide. So for the semicircular section, we can work out the second area moment about its base, xx, using our standard formula. We can do the same for the rectangular section, work out the second area moment about its base on xx. But for the triangle section, we'll need to work out its second area moment about its centroid location at tt. We need to work out the area of the triangle, and we'll need to work out its distance from its centroid location into the x-axis. And then we can use the parallel axis theorem to work out the second area moment for the triangle about xx. For your reference, we'll need to use the formulae associated with the rectangular section, shown in this row. We will need to use the formulae associated with the semicircular section, shown in this row, and also with the triangular section, shown in this row. I'd now encourage you to stop the presentation and attempt this exercise, but the full work solution is shown on the following slides. So here's exercise 8, commencement of the solution. I'm going to let you review the solution at your own pace. As I said, we're going to consider the semicircular section, the rectangular section, and the inverted triangle section. Exercise 8, solution continued. We can use the parallel axis theorem to find the second area moment of the triangle about xx, shown here. And finally we can calculate the second moment of area for the composite section about xx by simply adding up the I for the semicircle about x, the I for the rectangle about x, and the I for the triangle about x. Final value is 4,180 centimeters to the 4. And of course this answer is stated to 3 significant figures as stated in the question. I'll leave you with exercise 9 to attempt at your own pace. In a way it's a similar kind of approach to that of exercise 8, but it relates to an unsymmetrical I section. We've got to calculate the second area moment and radius of gyration about the xx axis for this unsymmetrical I section shown on the right. The answers are shown here for the second area moment and the radius of gyration. I will show you a hint on the following slide for your reference. Exercise 9. Suggested hint is to use a table construction to calculate the area of the 3 rectangular sections. We have the upper flange, the top flange, labelled as item 1. We have the web, rectangular section, labelled as item 2. And we have the lower flange, lower rectangle, item 3. To help structure your solution, you can fill in the table. And once the table is completed, we can use the parallel axis theorem to find Ix. As I said, I'm going to leave this for you to work out at your own pace. Here's the formulae we'll be requiring for the rectangular section. That concludes the presentation. Here's the bibliography used to help generate the presentation. Here's a very good engineering textbook for technician engineers. And I hope this presentation has been of use to you, and as always, thank you for viewing.